Thanks very much for the introduction. My name is Tongping. I'm from University of Hong Kong. Today I'm going to talk about my part of my PhD research work named Optimization of Tree Locations for Localized Cooling Sports in an Urban Park. As we may experience and learn from news, the heat waves are increasing everywhere around the world, and cities are looking for effective solutions for keep their urban areas cool. And a part of the important solutions is no doubt planting trees. And but how many trees do we need, and to what extent tree can cool our city air temperature? A recent study published in Lancet, they've indicate that if we increase the tree coverage in European cities to 30 percentage, and the air temperature will be lowered by zero point 0.4 to about 6 degrees Celsius. And they also found that 30 percentage can also lower the summer death rate by 1.8 percentage related to the uh, urban heat island effect. And some cities are setting much ambitious targets higher than 30 percentage. For example, the city of Melbourne and Singapore. But existing policies fail to mention where to plant trees. And the greenery cut targets at the city level or even the development site level, they are sometimes KPI driven indicators, are not inadequate to guide the real landscape design practice. And in research community, the literature review disagreed upon whether to concentrate trees in fewer locations or spread them out in a larger area of a big site. So far, knowing where to plant trees is still a challenge in both design practice and also research community. So there is a need for a refined understanding of the cooling benefits associated with the locations rather than their quantities. Since I'm living in Hong Kong, one of the most compact cities, what interests me is how we can achieve more cooling with fewer trees. The research question is there a systematic way to optimize tree locations for their best cooling performance? We developed a novel method to automatically location trees for their maximum cooling benefits, and a rapid simulation model was first developed and evaluated, and then to be linked with an optimization model. The model the model used GA as an optimizing algorithm, which can drive the design process towards a better cooling performance. And the algorithm mimics the species evolutionary process by selecting higher performing design options and combining the crossover and mutation produces new generations of design until optimal solutions achieved. As illustrated here, I will go through in detail about the two models. First, we develop a rapid simulation model. As I mentioned, we need because we use optimization algorithm and the objective function need to call frequently of evaluating the performance of each design solution. So it is a key to develop a faster prediction model that assess the tree cooling performance. And as we know that trees are excellent multitaskers, they cannot only reduce the solar radiation by shading effects. They can also lower the temperature by evapotranspiration. And also, they can modify the airflow passing through the canopies and also the moisture around the trees. So it is important to consider all the components of cooling mechanism. And our model can simulate all the cooling components of tree canopies in an outdoor space. And the method developed also runs reasonably fast, which can be linked with an optimization algorithm. Also, to evaluate the model performance, we did field measurement under tree canopies during the hot, temperate, and the cool seasons. We select 5 trees and put the whole weather station under the tree canopies, and we measure the air temperature, the humidity, wind speed, and also the solar radiation under the canopy. The second part is to develop the tree location model, and we map the design problem into a mathematical optimization problem, and then we use uniform tree canopy models as shown here. The green cubic geometry indicates tree canopy, and the tree locations were coded mathematically in 3 dimensions. And then the design options were defined as the possible combinations of the tree candidates, shown here as the white points. And we will use the image here shows the model domain, the 3D building geometry, and also the boundary conditions we used. And the design options will be defined as a possible combinations of tree candidates, and we also use design constraints such as the number of trees we need to plant and the setbacks from the buildings. The objective function here is set to minimize the potential heat stress from is set to minimize the potential heat stress. And I will move on to the results here. And after our model evaluation, a reasonable good agreement were observed between our simulated air temperature and the mirrored one. And we also do the model evaluation by observe the difference between the mirrored and the predicted one. And there's no systematic arrow here because the differences follow a normal distribution. That means there's no over and under predictions in our model. Also, we tested the performance of the automatic simulation-based design workflow. And the left-hand side image shows the cooling performance of every design solution, and the right-hand image shows the evolution of each design option. It shows that the objective function for coolest part of the tree rearrangement scenario appears to have been decreased towards a lower value across the fluctuation, and it took maybe 7 hours on an ordinary desktop computer to finish to converge to the optimal solution. And it's really a computational efficiency compared with existing methods. And the computational efficiency is the key to achieve to link the simulation model with the optimization algorithm. We also test the workflow in different scenarios in landscape design. First example is if we have a chance to rearrange existing, let's say 55 trees in my study site. And this workflow can automatically identify the optimal solution. And the insight is for better cooling. Trees are to be concentrated towards the leeward side of the incoming wind. But you may question me that it's not possible to rearrange existing trees. How about adding new trees. And also, our workflow can do this task. The workflow will tell us new trees at the right place, at the right location can cool 3 times than otherwise, as shown here. To answer my question, proposed in the very beginning, can we achieve equivalent cooling performance with fewer trees? The answer is yes. And two images here, the combination of tree locations, they have the same performance in cooling in cooling the human heat stress, but they have different tree coverage ratio. That means we may not need so many trees. Just to put our trees in their right locations can achieve better cooling performance. Also, another interesting finding is that optimized tree layout for cooling purpose can increase the lower corruption temperature spots shown as here. The overall distribution of simulated UTCI are distributed here. Uh, the figure shows the peak, the mean, and the interquartile of the distribution. The first two wave crests reflect the unshaded paving. The third and the fourth reflect the shaded paving. And the last crest showed the location shaded by both trees and flyover. To conclude, our developed method can automatically searching for optimal tree locations regarding their maximum cooling performance. Also, insight for landscape design, trees can cool the best if they concentrated towards the leeward side of the incoming wind. Also, we should put trees in their right place to achieve their best cooling performance. At last, the proposed method can inform research and also landscape design in the future concerning urban cooling as a target. And last, I wanted to thank Professor Jianxiang and Professor Qunshan Zhao. They offer great assistance in my study and really important insights. I'm really thankful for their contribution. And also, the study was published in a journal. And if you are interested to learn more about the details, please scan the QR code and you can read the full paper. Thanks for your attention.
Thank you. Do you have any questions? Yes.
Well, thank you for the excellent presentation.